Hello, today I'm going to be telling you about suspensions, electrolytes, non-electrolytes, the differences between a calorie, and a joule. First we're going to start with the calorie, and joule. See this? This is a chewy granola bar. It contains 100 calories, as you can see right there. As you can see, that bolded calories is capitalized. The capitalized calorie is a nutritional calorie, and all the lowercase calories, there are 1,000 of those within one nutritional calorie. So instead of 100 calories in here, the non-nutritional calories, there's 100,000 in here. And a joule, there's 4.18 joules per every non-nutritional calorie. So there's 418,000 joules in this granola bar. Makes you feel really fat. So next time, split your granola bar with someone. Alright, now we're going to talk about electrolytes and non-electrolytes. Well, an example of electrolytes would be pouring Gatorade powder in a mixture of water and then stirring it. The reason that it's electrolytes is because you cannot distill this and get... What is that? I don't know. You can't distill the Gatorade powder back out of it, and it also provides energy. Now, an example of a non-electrolyte would be taking some Morton salt and pouring it in some water. So you see, and then we stir it around, and the salt does dissolve, but it can be separated. Thus, if you boil the water will evaporate, but the salt will stay left behind. So that is a reason why that is a non-electrolyte. And lastly, I'm going to be telling you about suspensions. Well, a suspension is something that can be extracted, or it's basically two things within a substance, like salt water, as I've just made here. You've got the salt on the bottom and you've got the water on top.
The boiling point of water is 212 degrees Fahrenheit. The melting point of water is 32 degrees Fahrenheit, or 0 degrees Celsius. Water vapor, the gas form of water. Ice, the solid form of water. One of the uniquenesses of water is that you can see all three forms at the same time.
Hello, today we're going to tell you about universal solvents, solution process, water hydration, desiccants and effluences, and Brownian motion. Well, a universal solvent is a substance that dissolves most chemicals. Water is called a universal solvent because it dissolves more substances than any other solvent. This is our universal solvent, which is water. We are going to throw ice cream salt into it, and we are going to make a solute. Okay. And stir that around a little bit, thank you. A solute is a substance that's dissolved into a solution. For solutions of fluids, the solvent is present in a greater amount than the solute. The solution process are homogeneous mixtures of two or more pure substances for our purpose. We will generally be discussing solutions containing a single solute and water as a solvent. What is a solvent? Well, in crudest terms, it is the molecule in which the mixture with the highest concentration. Okay, now we're going to get this stuff boiling, and hopefully you can see the steam rising off of it. And we're going to talk about water hydration. Water hydration is chemically combined with a substance in such a way that it can be removed. As by heating. As we are heating it, we can take the water out of the substance, and we can leave the salt in the beaker. Now, desiccants and influences is the loss of a water. And influences is the loss of a water, or of crystallization from a hydrated or solvated salt into the atmosphere or an exposure to the air. Influences can occur in natural and built environments. This, which would be a built environment. And last but not least, our Brownian motion. It is the random motion of particles suspended in a fluid, a liquid, or a gas, resulting from their collision with the quick atoms, molecules in the gas or liquid. We're heating the liquid right now, so we can see Brownian motion, which is the particles moving and bouncing off of each other at high rates of speed.
You get closer. To the boiling part.
Suspended in a fluid, a liquid, or a gas, resulting from their collision with the quick atoms, molecules in the gas or liquid. We're heating the liquid right now, so we can see Brownian motion, which is the particles moving and bouncing off of each other at high rates of speed.
You get closer. To the boiling part. In a few seconds, it'll get into a rumble. It's called rumble. It's going.
It's done. We're done.
We're done.
Yeah, we're done.
Show me.
This experiment, it's like an example of heat of vaporization. You're supposed to get a 1,000 milliliter beaker, but we couldn't find one, so we used a 500 milliliter beaker. We put it up with water, we got a 10 milliliter graduated cylinder, fill that up to like about 6 milliliters of water, then we place it upside down into the water without the water spilling out. Now we're gonna heat it and just watch as the heat, watch as the air inside the tube expands and stuff. And you just gotta steer it. Yeah. And it takes about like 10 minutes, so I don't think we're gonna stop. Heat of fusion is basically melting. It's getting a solid back to a liquid. Yeah. Then you have to find specific heat for certain stuff, and to find specific heat, this is the formula. Yeah, can you see that?
Yeah.
This is heat mat. Yeah, no, heat added. This is a specific heat that you, like the ones that's supposed to be there. The mass of the object that's being heated and the change in temperature from beginning to end. What's being heated?
We need water vapor, and we'll come back later and we'll show you. See, you can see where the air bubbles at right now. Yep. Alrighty, we'll be back.
The hydrogen bond is a type of attractive interaction between an electronegative atom and a hydrogen atom bonding to another electronegative atom. This bond always involves a hydrogen bomb atom. That's false. Hydrogen bonds can occur between molecules or within parts of a single molecule. A hydrogen bond tends to be stronger than their walls forces, but weaker than covalent or atomic bonds. And I don't know what their walls forces is. Thank you about chemistry. I don't like the bomb.
What are you gonna do?
We don't need horse cleaning.
What are you gonna do about it?
Just show next
It's
year,
changed slightly. Not much, but what's this an example of again?
I hate it by vibration.
Heat of vaporization. Anyway, you get the gist of it. The air expands.
In the tube.
And it's gonna end up like bubble. Like bubble.
The fog or the steam is gonna be caught into the tube
Yeah.
and it's gonna be trapped in there because it doesn't have no place to escape.
Yeah.
And you can kind of see steam coming up from this water already, a little bit. From the
Mm-hmm.
don't touch it.
Yeah, so yeah. Today I'm going to be talking to you about the Tyndall effect, polar covalence, surface tension, and colloids. I'm going to start out with the polar covalent. A polar covalent is a bond between two nonmetals. And I'm going to show you an example of a covalent, carbon dioxide. And the way that I'm going to show you is by covering these flames with a glass cup. The flame inside's burning off all the oxygen that's trapped inside, and the carbon dioxide comes and blankets the flame, putting it out. See as it gets dimmer and dimmer? Flickers. Oh. Is it gonna come back on? Out you go. There it is. Okay. Alright. Now that we've got, now we've got polar covalence done, I'm going to show you surface tensions. A surface tension would be an example of putting pepper on top of water. The pepper is not as dense, so it doesn't really sink. And if you take your finger and put some soap on it, I'm going to show you what happens whenever you dip soap, which is a whole lot denser than pepper is, in water. Did you see that? Now it's all sinking on the sides. Looks pretty cool. Alright. Alright. Now, a colloid is something that is visible and can be separated. Well, it's a substance of two, and you can see through it. An example would be Gatorade. I can see through it, and it can also be divided. Oh, no. Salt water, I'm sorry. Salt water, or pepper water, is visible. See? You can see my eye probably. And it can be divided if you strain it or filter it. Alright. And another reason to show that, Tyndall effect, last but not least, is the Tyndall effect, which is the refraction of light through a colloid. Well, I'm going to show you what this does. Glass is also a colloid because it has tiny particles in it. As you can see, I put the light up to the ceiling and it's a circle. But whenever I put the glass in the way, it refracts the light in many different directions and creates all these cool shapes and patterns. Alright, there we go. Well, that's it for now. I will let you get back to your business, and yeah, good night.